In this video, I'm going to be talking about exponential functions, and these behave differently than other classes of functions you might be more familiar with, like linear functions, quadratic functions, other polynomials, rational functions. All right. I usually start discussions of exponential functions with this little puzzle, this little question. So suppose that you had saved a king's life, and suppose the king gave you a choice. You can, for your prize, you can either win, he'll either pay you $1,000 for saving his life, or he'll give you some pennies on an old chessboard. Okay? Now the pennies on this old chessboard are arranged in a very specific way. On the first square you have 1 penny, on the second one you have 2, on the next one you have 4, and then 8. So it doubles every time, basically. Okay, so the next square has twice as many pennies as the square before. Now, so which would you choose, the $1,000 or the pennies on the old chessboard? Okay, now think about that for a moment if you like. You probably think that this is a trick question, so you're probably guessing that you should choose the chessboard. Can you estimate, just a rough guesstimate, how much money do you think you'll have in total if you selected the pennies on the old chessboard? Maybe 2,000? Maybe 10,000? Okay. Well, it turns out that if you selected the pennies on the chessboard, and this really happened, you would have 184,000 trillion dollars. Okay. In other words, you would have 184,000 billion dollars. So in other words, you would have all the money that's ever been printed in the history of the human race. All right, more than all the money that exists in the world, that's ever existed in the world. All right. So a lot of people get surprised by that result, and the reason that they're surprised is because they underestimate how quickly exponential functions grow. They are insane growers. That's what's their claim to fame. Okay? All right, so that's what distinguishes exponential functions from the other functions I mentioned. They grow a lot faster. So what does an exponential function look like? So for example, 2 to the x power, 10 to the x power, 3 to the x plus 1, 4 to the 7 minus x. These are all exponential functions. Excuse me. Now, what makes something an exponential function is that you have variables for exponents, expressions involving variables for exponents. Okay? Let me show you what the graph of a simple exponential would look like. Like, for example, 2 to the x. So the graph of 2 to the x, we know it has to be growing. All right. We know that x to the 0, 2 to the 0 is 1. So we know it's going to go through the point 1. And we know that when x is 1, you're going to get 2. So putting that together, so you'll have, it goes through 0, 1, and 1, 2, and it quickly grows from there. So the graph is going to take off like a rocket. It's going to be something like this. Okay, so it has the x-axis as an asymptote, horizontal asymptote, and then it takes off from there. Now, because any number raised to the 0 as raised to an exponent of 0 is equal to 1, pretty much any exponential function that's some number raised to the x power is going to go through 1. All right. Let's say if you wanted to graph 10 to the x, okay, that is going to go through 1, and then it's going to shoot up a lot faster. Okay, but you can see it still goes through 1. Okay, so that's what they look like. These are exponential growers. Okay, you can also have exponential decayers. Let me show you what a graph of that one would look like. Okay, and what I mean by exponential decay is something like 2 to the minus x. Okay, so I have a negative in front of the x. All right, so let's think about what that one's going to do. So that one, it's still going to go through 1. And although when x is equal to 1, now it's going to be a half. So it'll go through those two black dots. And as x gets more negative, then it'll blow up. And as x gets more positive, it'll get smaller. So this graph's going to look something like this. So it's the reflection of the last red graph with respect to the y-axis. Okay? Now, the reason this is called exponential decay is because as x gets bigger, it's getting smaller and smaller, but it gets smaller painfully slowly. All right? You have to go really far to the right in order to go a lot further below 1/2. Okay? At x equal 1, you have 1/2 for this example. Okay? So exponential growth and exponential decay. You can also talk about two common bases that show up all the time, and these we often talk about and by the way, the number that is raised to an expression with a variable, that's called the base, if I didn't make that clear before. So in these examples, 2 to the x, or 2 to the minus x, the base in both of those is 2. Okay? You will often see mathematicians and scientists working with 10. It's so common that 10 is called the common base. Okay? Now, this is not going to be obvious to you right now, perhaps, but it's also useful to use this infinitely long irrational decimal, 2.71828, and there's more digits after that. But this weird-looking decimal is a natural choice for various reasons. Okay, this goes by the name of e, lowercase e. Okay, so that's the other common base, and this one is natural for various reasons, so it's called the natural base. Okay, just file those terms in the back of your head for now, and later on you'll see more of that. All right? And so the graphs of the common bases, the common base exponential function and the natural base exponential function will look similar to the example with 2 to the x. All right, it'll still shoot up as you move to the right, and it'll still have an asymptote. Okay. Now, what are the domains of these exponential functions? Let's talk about that. So, you can plug in any value for x. An exponent can be positive or negative or 0. So there's no limit on the domains. However, the range. Notice that the graphs never go below the x-axis. So the range includes everything greater than or equal to 0. And then I already mentioned that I have a horizontal asymptote. So we would say that the long-range behavior is that it approaches 0, either from the right or the left, depending on if you're talking about a grower or a decayer. Okay? And if you wanted to talk about the inverse function and to graph the inverse function, we're going to be talking more about this later, but exponential functions do have inverses. They're called logarithms, but I don't want to say too much about logarithms right now, but just know that the inverse would look like this green plot right there. Okay, so it goes through 1, 0, and it has a vertical asymptote of the y-axis. Okay? And also you can have, of course, an inverse of a common base exponential and an inverse of the natural base exponential, and that would still go through 1, 0, and It'll be similar, the inverse of those would be similar to the green plot, and it would be a slow grower as you moved to the right as well.